this works, then I will share screen, but I will also not go to the presentation mode because I need to write together with you. It means that I will be sharing the screen quite often. I mean switching on and off because it's not easy to use different applications at the same time. Let me start sharing. We start sharing. So I hope you see my screen. I left you with the statement that we discussed. You remember it was the discussion with Carol, and Carol stated that motion is not needed for relaxation. And many of you started that it is otherwise. And then I just answered that the first argument that motion is absolutely needed for relaxation is hidden in the statement that actually relaxation is a perfect tool to investigate motion, which is a kind of answer, playing with words. But later I try to explain why it is so. By the way, to give honor to Carol, I also said that the geomagnetic factor of something, I still do not remember, probably carbon, is 10 times smaller than proton, and maybe it's 4 times indeed, as Carol said. But we can always check it in the figures. Coming back to the concept, what relaxation has to do with motion. I told you that relaxation is the time which is needed for the system to get to equilibrium. To get to the equilibrium, the magnetic moments of the nuclei, if somebody in the waiting room, must take the proper orientation. I mean, such orientation, so it corresponds to the equilibrium state. And this takes time, and the changing of the orientation, the efficiency of the changing, is associated with the efficiency of exchanging energy with the surrounding. And I said that it's like giving somebody a courage to do something. You can do that by holding hands. Then there's magnetic dipole-dipole interaction, which stimulates, induces, encourages the transitions of the magnetic moments between different orientations, like that and like that. In the case of spin 1/2, it was not complicated. So here you have 2 water molecules, and there is magnetic dipole-dipole interaction between them. Actually, you can see that it is intermolecular interaction because those hydrogen atoms belong to different molecules. And if you ask me what is the reason of the fluctuation in time of this interaction, I would say that it is mainly translation diffusion. But again, this is a subject for later. Tomorrow, I'm supposed to give a lecture about falling into traps because of different models of motion. At this moment today, I only want you to convince that indeed you can learn something about motion from relaxation and show you the simplest way to do it. I will write a couple of equations, but as you see, I did not prepare any equations. So if I would be going to write complicated equations, I would need to be prepared before that. Well, as I'm not, it only means that I will write very simple equations, which is really promising. However, before I jump to that, I would like to tell you that the crucial quantity, the crucial phenomenon, actually, around which the whole concept of investigating motion evolves, is the concept of a correlation function. Well, what a correlation function is? The first question is, what is supposed to be correlated with what? And this is not a trivial question. to make it more close to this NMR science, I would say that the position of the molecules are the quantity which has something to do with the correlation. Look, we can walk faster, slower, but definitely will not go like 100 kilometers per hour, yeah? So if somebody asks me, like, meets me, let's say, at this time now, and say, oh, it's nice to see you. Where have you been 5 minutes ago? I do not want to say when I was 5 minutes ago. However, actually, my possibilities are limited because there. However, as I am now being in Olsztyn, if I say that 5 minutes ago I was in Warsaw, which is first from Olsztyn, you would hardly believe me. Because this is just impossible, taking into account the speed with which people can move. If you are between positions, it's like if you object is, it can be a molecule, a person, whatever. And you ask the question, whether this object was a certain time ago, like 1 hour, a second, a certain time ago, where this object was, if at present it is at this specific position. So let's put it like that. If the time which you are considering is short compared to the speed of the motion, there is a correlation. Actually, after all, if you ask me where I was 1 femtosecond ago and how it is correlated with my current position, well, I would need to answer that I was exactly at the same position. Because from the perspective of human movement, 1 femtosecond is something that we cannot notice. So the correlation between my current position and my position 1 femtosecond ago is 1. I am when I was. But then, if you ask me, let's say, whether there's any correlation between my current position and my position 5 years ago, I can lie as I like, yeah? There's no correlation because so much time passed that I could, I don't know, go all over the world. So correlation function is a function which describes how the system is losing in time the memory about its initial position. And the correlation function in some cases is exponential. You remember Adam's lecture about exponential functions. It is not all. It depends on the mechanism of motion, and this is more complicated stuff. But let's assume at the beginning that we consider the simplest case. In case of NMR relaxation, to describe motion of molecules, the question where the molecule is or where the molecule was is expressed somewhat different. For instance, I have external magnetic field, which is not plotted here. I have the axis connecting those two hydrogen atoms. And let's say at time 0, this axis was parallel to the magnetic field. Then after some time, it takes different orientation because of stochastic motion, stochastic rotational and translational dynamics of molecules. And now is the question. I can correlate the orientation of this axis with the initial orientation. I mean, orientation after some time with the initial orientation. I can calculate the distance between those two atoms after some time with the initial distance. It will change because of diffusion of those molecules. So this, and I can combine those two questions. I can also correlate the distance together with the orientation. So there's this kind of quantity which we try to correlate. And we are, instead of, for instance, correlating, the distance at which we are from a corner of our room, which is also this kind of quantity, we correlate this kind of values. Why so, and how it depends on mechanisms of motion is a difference. So let's say the magnetic interactions fluctuate in time. And because of that, in time, we are step by step losing the correlation. And usually this process is exponential. Okay, I got some info on Skype, sorry. So this is the first quantity which we consider. However, look, as I said, correlation function decays in time. So if I would need to plot a correlation function, there will be time on the x-axis and something which starts at 1 and then goes down. The thing is that relaxation experiment is related to the resonance frequency. Yeah, remember what resonance frequency is. The resonance frequency is the gap between the two energy levels, which we have in case of spin 1/2, but let's stay with that. So we have those two energy levels, and the gap between those two energy levels expressed in frequency units. Adriana, I cannot put the slide in full screen because I will like to write some. And there's not much on this slide. Coming back to the correlation function, as I said, we operate in frequency. We want to go somehow from the concept of correlation function, which is concept in time, to something which is related to frequency. And there is a mathematical trick, which is called Fourier transform. To be very sophisticated, one can say that it is like going from time domain to frequency. However, in NMR relaxation, the concept which we really use to express the relaxation rates is the concept of so-called spectral density, which is associated with the correlation function via this mathematical trick, which is called Fourier transform. You do not need to know. You do not need, it would be nice if you knew what Fourier transform is, but you really do not need to. What you should know that somehow if the correlation function is exponential, then the corresponding spectral density function is Lorentzian. Okay, you do not know, maybe some of you do not know how Lorentzian function looks like. However, we'll also come to this. So with this knowledge, let us try to think how to relate in a mathematical way the relaxation rate with the time scale of the motion. As I say, I will provide the simplest recipe. The recipe will be oversimplification, and you will learn in the course of time that it is not true. However, we have to start with something. This will be like, I would like to say that it will be approximation, but I have to say it's oversimplification sometimes. However, anyway, we have to start. So let me go with the first equation. And this is the reason why I didn't want to go to the presentation mode, because then I cannot write. So I will write equation. Relaxation rate is often called, almost always, R1. I will make the equation larger when I finish. So R stands from relaxation. 1, 1. It's for Pilates relaxation. It's just the first relaxation process. So therefore, it's R1. Well, on which quantities the relaxation rate depends? It depends on the resonance frequency. So let us put here resonance frequency. However, you see here that I wrote omega, which is typical symbol for angular frequency. So the frequency is not expressed in hertz, but in radian per second. In other words, it's just frequency in hertz multiplied by 2 pi, which is 6.28. Why? And I will write it down. But why I'm saying that? Because quite often one makes this kind of mistake. Then I said that the relaxation rate is proportional to the amplitude of the dipole-dipole coupling. The amplitude is associated with a quantity which is called dipolar relaxation constant, CDD, because it's dipole-dipole interaction, and C from constant. So CDD is a typical symbol for the prefactor which describes the relaxation rate. Actually, it might be nice to know that this prefactor, of course, decays, becomes smaller when the atoms, the distance between the atoms is large. This is obvious, yeah? There's no interaction if two objects are far, far, far away. But you might be surprised how strong is the dependence. It's like 1 over the distance power 6. So look, if the distance changes by factor 2, the coupling becomes weaker by factor 2 power 6, which is a lot. So in fact, only the closest surrounding of the molecule participates in the relaxation process. Then what we have here. Let me write the expression. Okay, I will be writing something you will not understand, but when I finish, it will take not much time. I think it will become clear. Now, okay. I have to click here. Now, see. 1 plus, and I will give you exercise. Down. Two plus 4 times yeah. So I'm very proud of the equation I managed. I hope you see it. So what is happening here? What is happening here? Let me put it here. I think I lost chat, whatever. Okay, I have chat now. To everybody, I cannot make it full screen because I will be not able to write. And I would like to construct those equations together with you. Something happened. Okay. Okay, I think I'm back. Okay. So this is this equation. What we can do? Well, first we need to explain something. So omega, and then you will be calculating. Omega is the resonance frequency in angular frequency units, which means it is frequency multiplied by 2 pi. Let me see. Then, what is tau c? Tau c is referred to as correlation. It describes the time scale of the molecular motion. So now, I will ask you a question. Before we start calculate, because I would like to show you that we can calculate some relaxation rates before you, depending on the time scale of the motion, before you get, before we start dealing with the relaxation game. So there is exercise for you. It's the first question. You see this expression in which units, I typed the question in the chat, in which units, maybe in another way, what are the units of the correlation? Who of you does to guess what are the units of the correlation? Seconds, for instance. It can be milliseconds, nanoseconds, femtoseconds, whatever, yeah? But they are just like units for time. Time is time. The fact that it is correlation, time does not change the units. What are the units of the relaxation rate? In which units you will express the relaxation rate? Second minus 1, reciprocal second. Yeah. Because the relaxation rate is the reciprocal inverse relaxation time. But then I have a question. If it is so that the correlation time is in seconds, let's say, the relaxation rate is in reciprocal seconds, what are the units of CDD? The bipolar relaxation cost. What are the units of CBD? Because units are, without the units, nothing makes sense. Okay, Carl is very active. The Hertz power 2, but why? What is Hertz actually? Hertz is 1/2. Yeah? Does everybody understand that? Why the bipolar relaxation constant is in Hertz? Power 2. Well, let me try to explain. I'm supposed to have relaxation rate. So, okay, the units of relaxation rate is second minus 1. Yeah? And this should be equal to what? Well, here I have quite complex expression, and we really also need to talk about the unit of this problem. However, here I have, let me put it like that. Yeah, here, equation, yeah. So I have, that will be second minus 1. Well, the correlation time is in second here. So to get second minus 1, I have to multiply by second minus 2. I'm not good at writing at this moment. I will improve it shortly. So it's like that times and equation. Yeah, and here I have second minus 2. Yeah. So my dipolar relaxation constant is in the unit second power minus 2, which means is Hertz power 2. But you know, before we start calculating, we should realize one thing. I told you that the resonance frequency, yeah, is for obvious reasons in frequency. But then I'm telling you a kind of strange thing, that relaxation rate is in reciprocal second. It means in Hertz. Look, frequency is also in Hertz. So this is quite often the first reason for confusion, because you have frequency in Hertz, resonance frequency, and relaxation rate in principle you also have in Hertz. Yeah, formally it is so. However, when it comes to the relaxation rate, in fact, nobody uses the units Hertz. Why? Because the original thought, the first thing which comes to your mind, is not really relaxation rate, but relaxation time. It's the more natural way of thinking, how long something takes. However, if I would like to write expression for relaxation time, I would need to write 1 divided by this whole thing. So the expression will be quite complex. So it's much easier to define relaxation rate, which is just the reciprocal relaxation time, and simplify the expression in this way. However, we keep in mind that this is reciprocal relaxation time, reciprocal relaxation time. So somehow it's a really psychological effect, which has not like saying that relaxation rates are enhanced. But formally they are, but you will never ever find it in any literature. So then I would propose that you perform some calculations, and then depending on what you get, I will solve also this problem for you, but I will give you like 5 minutes. So I would make it like that. Correlation time is 5 nano, maybe 50 nanoseconds. Yeah? Resonance frequency is 10 megahertz. Relaxation rate is, let me make it like that, 0.2 second minus 1, yeah? 1/2 is the same thing. Please calculate the dipolar relaxation constant. I suppose we can spend like 3-4 minutes in this way. I will be waiting for your answer. In the meantime, I can make it full screen. So you see better ones here. And you have the chat box in which the question was. If after 3 minutes nothing happens, I will give you the answer. It's not only about relaxation, it's about getting some ideas how to calculate things, how to solve this kind of problem. In principle, I could motivate you in this way that I could say that the person who we should have a kind of game, and the person who collects most points goes, I don't know, to a conference for free, but unfortunately, I'm bound by consortium agreement, which means that they needed to discuss such things in advance, what I did not. However, anyway, I hope you will try to calculate. Two minutes more. Ricardo said that it is 0.17 seconds. Ricardo, I'm not sure if the number is correct because I would need to calculate it, but for sure the units are not correct because we just already agreed that the units for the dipolar relaxation constants are second power minus 2. And you gave answer in seconds. So even if the number is correct, which I do not know, we'll calculate it together. The units are not okay. Regarding what Faisal posted, yes, you are right. We have to convert the resonance frequency to radian per second first. Carl says that it's 4 power 6, 4 times 10 power 6, in which units? Yeah, that's power 2. Yeah, because 1/2 is hertz. I don't know. Let me calculate. Okay. So I have to stop sharing because I have to switch to a tool which gives me this chance. I will just use ordinary Excel. So let me run Excel, and then I will switch to Excel to perform those calculations. Okay, then let me share the screen again. So you see Excel screen. Well, frequency. It's 20 megahertz. So first, frequency in hertz, because first I have to convert it to so-called SI units. I will make it larger. Everything. Yeah, so it's frequency and frequency in hertz. Well, it's 20 times power 6. Yeah. 20 times 1 million. And because 1 megahertz is 1 million hertz. As Faisal said, frequency in radian per second. It means angular frequency units. Yeah, this is equal frequency times 2 pi, which is 6.28. Okay, 6, comma. Depends on the settings of X. Then let me calculate when I have this expression. I will call it first. Let me use here correlation time. The correlation time was how much? I do not remember.
15 nanoseconds.
15 or 15?
50.
50 nanoseconds, yeah? 50 nanoseconds. Well, but I need correlation time in seconds. Always unit matters. So it's like
15 to 10 power minus 9.
Sorry?
15 to 10 power minus 9?
Yeah. So it's 15 times. Yeah. Because one must know that 1 nanosecond is 10 minus 9 seconds. Then let me calculate in the relaxation expressions the first step. How the first term looked like? It was like I was supposed to take the correlation time and divide it by 1 plus frequency times correlation time power 2. So this is the answer which I got. Yeah. Second step. The situation is similar. It's 4 times correlation time divided by 1 plus 2 times frequency in radians per second times correlation time in seconds power 2. Right? Okay, so I got this back. First plus second term, it's equal this plus this. Okay. Yeah. Then relaxation rate. Relaxation rate
0.2.
0.2. And bipolar relaxation constant is equal to what? Relaxation rate divided by this expression, yeah? So this is about 8 times 1, 2, 3, 4, 5, 6, 7. Power 7 hertz power 2. So this is more or less the answer. So who was right? Carol corrects me that actually the frequency was 10 megahertz. Okay. Let it be. So this is your answer. So here should be, let's say, 2.1. Yeah. You see, it's not a very big. I was mistaken in the frequency. I just corrected it very easy. What can I do? In this way, I more or less learned what is the order of the bipolar relaxation constant because there are typical values of relaxation. So let's make another trick. Let's assume that I would like to understand how relaxation rate changes with the resonance frequency. Let me start from 1 kilohertz. And I can extend. So if I go like that, I'm doing this in hertz. This is my frequency. You see, I can make it until 100. Will have huge range. No, not really, because this system has something strange. I have to do it again. That's what I do not like about Excel, because you know it adds just. Here I have to make 4, 3. And in such a case, now it should. Let's make it different. Remove. And okay, let us make it like it will be even better. Frequency in hertz. Yeah, and now I know. And here is equal times 1.2, let's say. And now I think I will be able. Okay. Now I should be able to generate a certain frequency range. Let's cover here. 37. Here I have. Yeah. I would like to get 100 megahertz. So this is what I already have here. Yeah. Because 100 megahertz is 1 in power 8. Now, okay. Then I want to have frequency in angular frequency units. It means radians per second. This is actually very simple. I can make it equal to this times 2 pi. Sorry, I have to do something with this. Okay, I forgot that it accepts only comma. No, okay. Done. You see also, I suppose everybody uses Excel, but in explaining this concept of how to calculate it, I can also, show you this tool. So maybe also. Then I need correlation time. In seconds. So let me make it 10 nanoseconds, which is 1 minus 8. Then bipolar relaxation constant. We got like 2 power 7, we can make it 187. Yeah. To keep it just for the right order. It is, of course, in hertz power 2. So let us now proceed with the calculations. First, it is equal to what? Correlation time divided by 1 plus correlation time times frequency power 2 by close. And if you know a little bit Excel, if I now extend it down, it will change not only B2 to like B3, B4, but it will also change N1 to N2 and so on. And I want to keep the correlation time unchanged. So I have to fix the columns. I mean the cells, not the column, which I do by putting dollar in front of it. What I did, here I have that, but you see, here I have also, I have B3, here I have B2, here I have B3, but everywhere I have N1. You might be surprised that this number did not change. And it still did not change. And it still did not change. And still did not change. Changed a little bit. And eventually changed. Why it did not change at the beginning, I will explain when I finish this case. Second, is equal 4 times correlation time divided by 1 plus 2 times frequency times correlation time power 2 close. However, here I had again put the dollar sign. My cut is also again back. Okay. Yep. Then I go down. It doesn't change. It doesn't change. Please believe me, it will. And it did. And here I have the sum. Yeah, first term plus second. So I have this plus that. Okay. And here, if you remember the expression, it's relaxation rate in second minus 1. Minus what I'm supposed to do to get the relaxation. Actually, I should multiply the sum by the dipolar relaxation constant. Yeah, done. If I take the dipolar relaxation constant larger, let me add 2 more zeros, this quantity will be also larger. It will start with 50 and so on. If I change the correlation time, this quantity will change as well. So in this way, I can try to simulate the relaxation rates. But what happens now? Let me copy that. Copy. I will switch off the sharing only for the purpose of running origin. This is what Carol showed you at the beginning. Because I do not like to make figures in X. So I'm running now origin. And now I will share screen. So now I'm sharing screen again. Yeah, see the origin file. And I paste here all those things. And then I will make a figure. I will plot the relaxation rates versus frequency. Looks strange. Well, here I would claim that we have frequency in hertz. Then I'll make a trick. I will use logarithmic axis. That, and the axis is logarithmic. You see, a lot of. I can also put some effort for this figure to look better. I might say that this is not worth, but somehow a little bit of aesthetics. After all, you need to write papers. Then I can write relaxation rate in seconds minus 1. We do not like to call it hertz. And you have your figure. If you like, we can also make here logarithmic scale. Sometimes we do, sometimes not. This was not intelligent from my side. Let me change the name. Let's do match. Here I have. Yeah. So I decided to choose logarithmic scale on the x-axis. On the y-axis, I can choose logarithmic or linear scale, whatever I like. It depends on the purpose of the applications. But this is how it works. Then, before I show you some experimental data, I would like to ask you, who of you knows why at low frequencies, low magnetic fields, the relaxation rate is frequency independent? Because then it changes strongly. But why it is frequency independent? We have something in chat. Carl says that the correlation time times the resonance frequency is much smaller than 1. And this is the yes. Let me again change to that, because I have many screens. You know, this is this effect that here, yeah, those terms here, here, were frequency independent. Because, again, when I look at the expression, I do not like this constant switching. If I look at this expression, this product for short time or small frequencies is much, much smaller than 1. So it does not matter. So you can neglect it, and only those terms count. Then, when the frequency becomes larger, then of course those terms become more and more important. They approach 1. Eventually they became much larger than 1. And of course, this relaxation rate very much depends on the resonance frequency. let me put it in this way. In fact, I wanted to show you one more thing, but maybe you have questions too. So I will ask a question. Okay, you can try to solve it yourself. I will again give you some time. If it does not work, but I believe it will, then we'll do it again. So, resonance requires 10 megahertz. At which correlation time the relaxation rate reaches maximum? Is the maximum reaches extreme, which is maximum or minimum. So at which correlation time the relaxation rate reaches an extreme? Because now we perform relaxation experiment at one frequency, for instance 10 megahertz, and we change temperature. When the temperature goes down, becomes lower, the molecular motion becomes slower. So the correlation time becomes longer. This is what Adriana said at the beginning when I asked whether there must be a motion for the purpose to observe relaxation. She said yes, and then she stated that actually the system may not be at 0K. I said yes, because at 0 Kelvin there's no motion. However, we are not going to approach 0 Kelvin. Actually, it will be a challenge by itself. However, we can heat up or cool down our sun compared to the room temperature. And the question is, whether there is such a correlation time at which, when the resonance frequency is 10 megahertz, you have a chance to reach an extreme of the relaxation. How would you approach this problem? I know that everybody is tired, but I promise this is the last task for today. Now I want you to reach this level so you are independent in such calculations. So you always can get some. Of course, there are better solutions than using Excel or Origin. However, if you do not intend to write any software, after all, this is only a tool for using for different applications, not a subject itself, then it's sufficient to be able. Carl says that at -9 seconds we reach maximum, and -5 seconds we reach minimum. I will try to calculate. I do not have opinion about that, as long as I as long as I calculate it, then I will have opinion, let's say. But there's one thing for certain. It has maximum or minimum. It cannot have both. So something here is not right. So let me share screen, unless there is another answer. Do not hear any. So again, sorry, I first have to find my Excel. It seems that I like Excel a lot. So let me share. Okay, I do have it. So now, correlation time. In seconds. Well, we can start from very short correlation times. Let's say of the order of 1 picosecond. And we will increase the correlation time. As you can see, I have the same problems because it does not understand. It does not understand that I want it to be multiplied. But maybe it does now. Yeah. So let me continue. So the time is getting longer and longer. So in this way, I'm mimicking the temperature going down. I suppose that I can stop at minus. Okay, so this is my correlation.
Para quem vê o mundo através.
Sorry, I didn't hear. Sorry, it was a question.
No, it was English.
Okay, I varied the correlation time between -12 and -10 -12 and 10 -5. So looking at the typical motion of molecules, -12 is a very fast motion, -5 is a very slow motion. Then I have here resonance frequency in radians per second. And to make my life easier, I will implement it already. So this is equal to 10 times 1, 2, 3, 4, 5, 6 times 6.28. Okay, again, forgot that it is called. Okay, so this is our resonance frequency. So, first step. Please take into account that I do not consider here the bipolar relaxation constant because it's of no importance. I mean, it only multiplies, it only scales the relaxation rate, but does not change its shape. So what I have here, correlation time divided by 1 point dot times dot to close. And here I do not want to change the frequency. So this is the first time. Second. Four times correlation time divided by 1 plus 2 times that times that power to close. And this one is to not move. So I'm fixing. Done. Relaxation rate. Okay, as those values are large, I can use the polarization constant, but it does not change anything. It's just only to rescale things. So let me use it like it will be easier. Yeah. So then what is my relaxation? Is this times first term plus second term. Of course, here I'm locked. You know, if I would not use this paper relaxation constant, I will have here minus 12. It does not matter. Yeah. So I calculate it. Let me now plot. I have my, yeah, and okay. So now I will put it here. I could plot it in Excel. I strongly dislike. Yeah. And let me plot it. Strange thing, yeah? Let me also use here logarithmic scale, and after all, I started from minus 12 and finished like correlation time in seconds. Relaxation rate in second minus 1. Unfortunately, it seems that I did not record it. Maybe I don't know. And I have maximum here. How did we do it? Yeah. So it's more or less at 8.5 minus 9. And it reaches maximum. Oh, it's recorded. So, what do you have to say? As I said, the relaxation rate depends on type of relaxation. So I'm very new and I need more information to calculate. You are, of course, right. But in this sense, that the expression for the relaxation rate depends on the relaxation type in the sense of the interaction which caused the relaxation and in terms of the mechanism of the motion. Because for most of dynamical processes, the correlation function is not exponential, which means the expression is steep. However, here I just only wanted to demonstrate how to solve this kind of problems. So therefore, I have chosen for the beginning the simplest relaxation expression. By the way, we will choose it very often because it helps to approximate the time scale of the motion on the basis of the relaxation rate, which you will measure. And as you can see here, this quantity cannot have maximum and minimum. So this is the story which I wanted to tell you today. We have still like half of hour to spend together if we like. This is not an obligation. I think Leonardo left us. I hope Adam is here. Adam, are you there? He does not hear me. I don't know.
Actually, yes, I was here, but I needed to unmute myself.
On your microphone. So it's up to you. If you have any kind of questions, we'll be happy to answer. This is an interesting question, Carl. I'm not catching it. Maybe because I'm tired. Well, it might be so. This Gaussian leg curve is having two minimas before it went to zero. Why? I'm not catching it because maybe I'm tired. Actually, this is not Gaussian leg curve. This is Lorentzian curve. Because you have sum of two Lorentzian functions, which is they are shifted on and beat, and this is very much a Lorentzian function. So this is not Gaussian. Gaussian curve looks completely different. It's not like that, such a bump. But does not matter this thing. Why do you think that we have two minimas before it went to zero? Actually, it never goes to zero, by the way. Where do you see two minima? Because this curve just goes up. Let me show it again. And this curve does not have any minimum. It has only maximum. Maybe if I make here logarithmic scale, although never did not cross my mind that it might be a kind of, yeah. Okay, but it seems that it might be. Let me change it. Yeah. In this representation, we clearly see that it does not have any minima, although one could see it also in the previous one. It has only one maximum. I hope I convinced you. Oh, there is a new question. On this scale, it looks okay. Okay. Yeah, it might be a kind of optical illusion. It does not have meaning. Is there more questions? Or should I wish you nice evening and see you tomorrow? If this is so, have a nice evening and thank you very much. Pedro, I stopped, I don't know what I did, but you were not there. I stopped recording, then I started recording, and the recording is in progress now.
Yeah, and I can stop